So after completing the Work and Power lab, which is the one you did while walking and running up the stairs, you probably found some interesting information about work. When we were answering these two questions initially, do you do more work and do you do more power when you climb the stairs quickly or slowly? Probably most of us answered the question that you, of course, did more work and used more power when you climbed quicker, right? That just kind of makes sense. But what we found out is that the work stays the same, whether you climb fast or slow, and only the power changes when you change your speed. This is because of the equation. When we take a look at work right here, work is equal to the force times the distance. Every time that you climb those stairs, it's the same amount of force, and it's the same amount of distance. The force is the force that it requires your body to move, meaning how much weight you have, meaning how much force due to gravity you are countering. That doesn't change whether you're moving fast or slow. You always weigh the same, and therefore force never changes. The distance also doesn't change. Whether you're going up the stairs 1 at a time, 2 at a time, or 20 at a time, you're going up the same number of stairs. So because these don't change, work never changes. Work is the amount of energy used to do something. That's not going to change if you do it fast or slow. What's going to change if you do it fast or slow is this time factor right here. The faster I do it, the smaller this amount of time. And the smaller the amount of time, the bigger the power, meaning the more power that is required to do this work, meaning the more power that is required to use this much energy, how quickly that energy is burning up. So if we think of work as energy and power being how fast that energy is burning, we know that whether I hike 1 mile or hike really fast that 1 mile, I still burn the same number of calories. One of them just took me 15 minutes, and one of them I was able to dawdle and go slow, and it took 30 minutes. I still walked the same distance, so I burned the same number of calories. One of them just took me twice as long. So when we come down to writing down here, we've got 4 paragraphs that we're going to do. Lucky for you, your science teachers kind of divided this up into specific questions. Now remember that for any lab report, your paragraphs should not just be specific answers to each of these questions, but it should be tied together in a paragraph. In paragraph 1, we're explaining why it was the same amount of work but different amounts of power when we climbed quickly or slowly. We should refer back to the graphs, and we should definitely be referring back to the equations. Since the equation for work is force times distance, and power is force times distance divided by time, we need to be making reference to how the force never changes and the distance never changes, but the time is the thing that changes. In particular, this also means that we should talk about when we go slowly, quickly, and quickly 2 stairs at a time. There are 3 different scenarios that we tested here, and therefore you should talk about all 3 of those right in here. In the beginning of this video, where I was introducing the idea of work and power, that would be some good explanation that you could take and put into your own words and use here, right? That the force stays the same, the distance stays the same. It's important to explain why the force stays the same. Another important thing to do before you start writing this is to watch the chapter 4.1 video on work and power, and to understand why work doesn't change whether you go fast or slow and what work is, right? And you can think about the hiker example that is in that video when the hiker is going straight up versus around and around. Many of us, when we're thinking about power, we're often thinking about electricity. Your light bulbs all have a wattage on them, which tells you how quickly they burn through energy. Generally, the faster that they burn through energy, the brighter they are. Now, of course, they've come out with LED lights that are a lower wattage, meaning they burn through less energy per second, but they're just as bright. They have as many lumens. That's a slightly different technology, but the idea is the same. The higher the number, that means the more energy that they're burning through every second, and generally that means a more powerful, brighter light. So this question is asking you to compare yourself to a machine. A machine is anything that does work for us. So a light bulb is technically a machine because it's doing work. It's doing electrical work and brightening up the room around us. It's moving currents through those wires, through those filaments. So we're comparing the work that you did to a 100-watt light bulb when you moved slowly, when you moved quickly, and when you moved quickly 2 stairs at a time. So if you could take your energy and convert it to electricity, how many 100-watt light bulbs could you keep burning during your climb? How many could you keep burning when you were moving slowly? How many could you burn when you were moving quickly? And how many when you were moving quickly 2 stairs at a time? Then this next question asks, could you sustain this power for as long as a light bulb could? The answer pretty clearly should be no, right? While you might have been able to generate as much electricity as 6 100-watt light bulbs when you sprinted up the stairs 2 at a time, you probably couldn't continue that sprint for very long. You would get tired. But a light bulb doesn't get tired. Yes, it eventually burns out after thousands and thousands of hours, but could you sprint for 1,000 hours? I couldn't. Could you even walk up the stairs slowly for 1,000 hours? Probably not. So this tells us something, which is this 4th bullet point. It tells us something about comparing human energy output compared to machine energy output. We build machines for a reason, right? Machines do work, and they do work that makes it in a way that makes it easier, more repetitive, and we don't have to do as much. So combining all this together, again, remember, you can't just answer each of these 4 questions singularly. They have to be tied together to kind of make sense. This is all building an argument right here in paragraph 2. Paragraph 2 is asking you to think about how you differ from a machine. Right? We might be able to produce more energy at one time than some machines, but can we do it for as long as those machines can? Paragraph 3 here is asking you to revisit that method that you experimented with. So you might have made yourself heavier by carrying up a set of books up the stairs. You might have made the distance longer by going up 2 flights of stairs, or made the distance shorter by only going up 3 stairs instead of 10 stairs. You might have jumped up 4 stairs at a time rather than climbing up those 4 stairs one at a time, right? Doing all 4 at once. Whatever your method was, you now want to think about why is it that that resulted in more power or less power. You're of course welcome to talk to your teachers about this, but you should go back to the 2 different equations, right? Work equals force times distance, and power is force times distance divided by time. So which of those variables did you change, and why did or did it not result in more or less power? But if you made the distance twice as long, while that should make the numerator bigger, what else did that increase? It probably increased your time. So the farther that you had to travel, yes, that made the numerator bigger, but it also made the denominator, time, bigger because it took you longer to travel that further distance. Potentially, traveling a shorter distance where you only traveled 2 stairs, you were able to do that significantly quicker than even just 5 stairs, right? So while the numerator might have gotten a little bit smaller, the denominator might have gotten proportionally even smaller because you were able to hop really quickly up those 2 stairs. So think about what variables you're changing and how that might impact the other variables when you're analyzing why it did or did not result in a higher power output. And then we want to take this one step further. Again, we're asking another question. Okay, so we already tested moving slowly, we tested moving quickly, we tested moving quickly 2 at a time, and then you tested whatever you did here that you talked about in paragraph 3. What else could we test to figure out how this experiment could be changed and more or less power be created? You should go back to the original planning that you did when you were coming up with your alternative method. How could you change the force? How could you change the distance? And how could you change the time to see the different effects? In this case, you don't have to be, your goal doesn't have to be to create more power. If you want to see the effect of going with a much greater distance but going 3 stairs at a time, you can do that. You can manipulate things just to see what would happen. It does not have to be with a goal of more power. It could just be to see what happens with the power. Get creative, but remember that we are experimenting, as part B says here. This experiment must build directly on the stairs lab, and therefore be completed on stairs. So don't go create a totally different experiment where you're running up and down a hill or you're paragliding or something like that. It needs to stay on point. Finally, you should write 2 single single sentence answers to the original problem questions right here. The original problem questions were these. Does it take more work, and does it take more power to go quickly or slowly? So you guessed, you had hypotheses right here, up here. Now you're giving your final answer down here. So when you're writing these 4 paragraphs, these bullet points are here to help guide you. You should be answering each of these questions, but you also must be tying these questions together so that the paragraph makes sense. If you're just answering the questions and not tying it together, then it's not a paragraph, it's just bullet point answers. What I recommend is, as you read this question, click there and hit enter and put your brainstormed rough draft answer underneath it. Then do this for this question, then for this question. Once you have enough info, go back and delete the questions out, right? You want to erase these things. You also want to erase paragraph 1. Then you tie that all together and make a paragraph. What you're going to turn in will be a 4-paragraph essay. It should not have a paragraph 1 header, and it should not be bullet points. So I'm going to put that here again. No paragraph headers, no bullet points. It should be 4-paragraph essay, right? In that 4-paragraph essay, you're going to have 1, 2, 3, and 4 paragraphs, right? No bullet points, no paragraph headers. All of this stuff should be deleted. Your conclusion will just be 1 sentence and a second sentence. You're going to turn in this whole Word document. So this whole Word document will have 2 hypotheses. It'll have a testable hypothesis here. It'll have all of this data filled in. It'll have 2 graphs right here, right? Graph for work, graph for power, and then it'll have 4 paragraphs. I'm going to go over that one more time just so we don't miss it. You're going to have your name, 2 hypotheses, your third hypothesis for the one that you came up with, data, more data, graph for work should be inserted right here, graph for power should be inserted right here. You're going to have your 4-paragraph essay and your 2 conclusion sentences.